So I want to finish the notes that we started in class. We were talking about whether or not a publican, the bartender of the pub, is short pouring customers. Now, we got through the hypotheses that the publican is not shortchanging, that the average pour is legal, so mu is equal to 20, mu being the average of all pours that the publican pours. The alternative is that the publican is shortchanging customers, so mu is less than 20. That's the hypotheses phase of this process. Next, we have the conditions, and we went through this already as well. The random condition, we can assume that this is a representative sample, barring perhaps issues of that we discussed in class. 10% condition, maybe they're independent, maybe they're not, but 20 is certainly less than 10% of all the pours that this publican would pour, and that's fine. And then the big one, though, the big new one, is the fact that we need to check whether or not the histogram of our data, which I've sketched here, is sufficiently normal. The histogram of pours is unimodal and sufficiently symmetric. You must include sketch. This is an important point. It's not enough to just say that the histogram of pores is sufficiently unimodal and symmetric. You need to show that that's the case. All right, so the conditions are satisfied. The conditions are satisfied to run a one-sample t-test, as we have been calling it in class. Using and now this is where we're getting to the notes that we talked about, using a t-distribution. We're not using a normal distribution anymore because, as we found, a normal distribution is not always applicable, is not always, doesn't always work. T-distribution with, now, the degrees of freedom. I mentioned in class that the degrees of freedom is always one less than the sample size. We had a sample size 20 in this case, so our degrees of freedom is 19. So to give a picture, then, the actual distribution that we're looking at, sample size of 19, would be like this. Now, the resolution in the video might not be quite good enough to see, but there's a little bit of a gap up here on the top. There's a little bit of a gap down here on the tails. The tails are a little bit thicker than the normal model. So this is why we need to use the t-distribution and not the normal distribution, because they're not really the same thing. All right, for the mechanics now, the mechanics phase, going with our way to test hypotheses. We write the statistics using the proper notation. We know that there are 20 pours. We have the data in the calculator, so doing the 1-bar stats for that list gives me an average of 19.845 and a standard deviation, sample standard deviation, keep in mind, of 0.1986. Use the sample standard deviation. Now we want to find a t-score because this is a t-test. Same way that we usually do this. 19.845 for y bar or x bar, doesn't really matter, minus 20, so the statistic minus the parameter divided by the standard error. Because here's the thing, we're talking means. We're talking about the average of 20. I'm not going to use 0.1986. 0.1986 is incorrect. I would not use that number by itself. What I'm going to use is this formula right here. Because I'm talking about the distribution of means here. I'm talking about, or I'm trying to figure out how far does the observed mean, or how significant is the observed mean compared to the expected mean? How significant of a difference is that? The disadvantage, though, is I don't know this. I don't know the standard deviation of all of the publican's pours. I don't have that information. So I can't find the standard deviation. I can't find the standard deviation of x bar. So I do the next best thing and find the standard error of x bar, which uses s instead of sigma. So I'm going to use then the sample's standard deviation, not the population standard deviation, because I don't know that. I don't know the population standard deviation. So it's not going to be 0.1986. It's going to be 0.1986 divided by the square root of 20. Because standard error here, again, standard error for y bar is going to be s over the square root of n, over the square So we do that. We get 1.9845 minus 20, and I divide that, 19.845 rather, minus 20, get negative 0.155, so this, I'll do up here, negative 0.155, divided by that whole thing, so divided by 1.1986 over square root of 20, meaning I get a t-score divided by 0.1986 over the square root of 20, a t-score of negative 3.49. So I'm looking as my p-value, what's the probability that t with 19 degrees of freedom is less than negative 3.49? So given that I expected an average pour of 20, the probability that I actually observed an average pour of 19.845. That or more extreme. Now, 3 standard deviations away, standard errors away, that's still significant. Even on the t-distribution, that's still going to be a significant difference. But to figure out exactly, we use now t-CDF, not normal CDF. T-CDF, because we're talking about the t-distribution. We do it the same way, negative 999 to negative 3.49, and now we specify the degrees of freedom. That's the other thing that we need to add to this. We're using the t-distribution, so same part, same initial part, negative 999 to negative 3.49, but now because the shape of the t-distribution changes with the sample size, we need to specify the degrees of freedom. So we have the degrees of freedom, we do that, t-CDF negative 999 to negative 3.49 with 19 degrees of freedom is 0.0012. 0.0012. That's our p-value. All right, we found our p-value. The p-value is low. 0.0012 is lower even than a 0.01 significance level, which we didn't specify, and we definitely should have. So that was a mistake not to do. But continuing on, we reject the null hypothesis. There is strong evidence that the pub owner is underfilling pints. We've rejected the null hypothesis, so now the natural question is to, well, if it's less than 20 ounces on average, then how much is it? So we're going to do a one sample t test. So y bar 19.845 plus or minus, we'll come back to that, times the standard error 0.1986 over the square root of 20. Now, getting the degrees of freedom. A couple ways to do that. There's a table in the back of your textbook, and you'll get a copy of this table in class that will essentially give all the different t-stars for all the different possible confidence levels you would want. It's going to look something like this, though, if I can get the link to process, get rid of my dots. There we go. So probably you're not going to be able to see this. Maybe you can see it now, but table of critical values for students' t-distributions. Column headings, probabilities, alpha above the tabulated values. Alpha of 0.4, 0.25, 0.1, 0.05, all the way down to 0.0005. If I want to do a 95% confidence interval, keep in mind what that would mean. 95% confidence means 95% in the middle, 0.05 on one tail, 0.05 on the other tail. But this is, so we're looking at then 0.05. 0.05 now for 19 degrees of freedom. 0.05 for 19 degrees of freedom would be right here, 1.729. 1.729, that is our degrees of freedom for, or our critical value for a 5% significance level, or 95% confidence level. No, that's wrong, isn't it? It's 0.25. Because if it's 95% at 5% significance, then that means we would want 0.025. Never mind about that. 1.85 then, right? 0.025? Nope, this one, boy oh boy. This is just a shambles, isn't it? 0.025, 19 degrees of freedom, 2.093. There we go. That's the number that I'm going to use. 2.093. 2.093. 2.093. All right, so finally, 19.845 minus 2.093 times 0.1986 divided by the square root of 20 gives me 19.752. Then all of that plus 19.938. And so we can say now, finally, I'm going to make this bigger. We are 95% confident that the publican is pouring an average, very key word right there, average, very, very key word. Make sure that you forget that, or don't forget that. Average of between 19.75 and 19.94, we'll say, fluid ounces of beer per pint. Okay? So that would be our final answer. Make sure that you include a confidence interval whenever you